One splits atoms apart, the other fuses them together. Both unleash power beyond imagination. Fission built our nuclear age. Fusion fuels the stars. This is scientific facts, and today we explore the energy that could save us or destroy us. The story begins in 1938, when German chemists Otto Hahn and Fritz Strassmann bombarded uranium with neutrons. To their surprise, the uranium nucleus didn't just absorb the particle, it split into two smaller nuclei, releasing more neutrons and a flood of energy. Lise Meitner and Otto Frisch, working in exile, realized what had happened: nuclear fission. For the first time, humanity had found a way to tap the binding energy of the atomic nucleus. The scale was staggering. A single fission reaction released millions of times more energy than a typical chemical bond. And because the process emitted extra neutrons, it could sustain a chain reaction, splitting atom after atom in a self-amplifying cascade. The physics was undeniable, but the implications were terrifying. World War II accelerated the race to harness this discovery. The Manhattan Project brought together thousands of scientists in secret, building the first nuclear reactors at Hanford and Oak Ridge to produce weapons-grade plutonium and uranium. In July 1945, the first controlled chain reaction was tested as a weapon at Trinity, New Mexico. Weeks later, Hiroshima and Nagasaki were destroyed, and the world was forced to reckon with the dawn of the nuclear age. But fission was not destined only for war. Even before the bombs fell, scientists like Enrico Fermi imagined reactors that could harness the same chain reactions for power. In 1951, the world's first electricity from nuclear fission was generated in Idaho. By the 1950s and 60s, nuclear plants spread rapidly, marketed as clean, limitless energy. The slogan, "Atoms for Peace," promised a bright future. The reality proved more complicated. Fission reactors could generate immense power without carbon emissions, but they left behind long-lived radioactive waste, some isotopes hazardous for tens of thousands of years. Safety was another challenge. While most plants operated without major incidents, the world never forgot the disasters. 3 Mile Island in 1979, Chernobyl in 1986, Fukushima in 2011. Each left scars on the public imagination. Fission gave humanity a fire it could hold in its hands, a source of energy that could light cities or annihilate them. It was powerful, but never free from fear. If fission was discovered in a laboratory, fusion had been blazing overhead for billions of years. At the core of the sun, hydrogen atoms are crushed together under immense pressure and temperature, fusing into helium. Each reaction releases a tiny burst of energy, but multiplied across trillions of atoms every second, it fuels a star. Fusion is nature's power plant. Steady, luminous, and capable of lasting for billions of years. Scientists first proved this process in the 1930s, when Hans Bethe worked out how stars shine. But if fission could be weaponized within a decade, fusion would prove harder to tame. Its first use came not in peaceful reactors, but in the most destructive weapon ever built, the hydrogen bomb. Tested in 1952, it unleashed energy not just from splitting atoms, but from fusing them, a force 1,000 times more powerful than the bombs dropped on Japan. The challenge was clear. Fission was relatively easy to start, requiring a chain reaction in uranium or plutonium. Fusion, by contrast, demanded stellar conditions, temperatures of over 100 million degrees Celsius, and pressures strong enough to force atomic nuclei together despite their mutual repulsion. Creating a miniature star on Earth was far harder than splitting heavy atoms. Still, the dream was irresistible. Fusion promised almost limitless energy. Its fuel, deuterium and tritium, forms of hydrogen, could be extracted from seawater or bred in reactors. Unlike fission, it produced no long-lived radioactive waste. And unlike fossil fuels, it released no carbon dioxide. Controlled fusion could power civilizations for millennia. By the 1950s, Labs in the United States, Soviet Union, and Europe began experimenting with magnetic bottles called tokamaks and stellarators, trying to trap plasma hot enough for fusion. Progress was steady, but painfully slow. Reactors could heat plasma, but not for long enough to yield more energy than they consumed. Fusion is always 30 years away, skeptics joked. A moving target that never seemed to arrive. And yet, recent decades have brought breakthroughs. The ITER project in France, the largest tokamak ever built, aims to prove net positive fusion power within the 2030s. In the United States, the National Ignition Facility achieved a historic milestone in 2022, briefly producing more energy from a fusion reaction than the lasers used to trigger it. Private companies, backed by billions of dollars, are pursuing compact designs with superconducting magnets, hoping to deliver commercial reactors sooner. Fusion has always been the fire of the stars. Whether humanity can bottle that fire safely on Earth remains one of the greatest scientific challenges of our age. Fission and fusion are often mentioned together, but in practice, they are worlds apart. One is the technology we already live with, proven, powerful, and problematic. The other is the dream that could transform our future if it can ever be tamed. The differences begin with fuel. Fission relies on heavy, unstable elements like uranium-235 or plutonium-239. These must be mined, refined, and carefully controlled. Fusion, by contrast, feeds on the lightest element in the universe: hydrogen. In particular, two isotopes: deuterium found in seawater and tritium, which can be bred from lithium, provide the ingredients for reactions similar to those in the Sun. Where fission fuel is finite and politically sensitive, fusion fuel could, in theory, be abundant for millions of years. The byproducts tell another story. Fission leaves behind a toxic legacy: radioactive isotopes such as cesium-137 and strontium-90, some of which remain hazardous for centuries. These demand storage in deep geological repositories, a challenge no nation has solved perfectly. Fusion, on the other hand, produces helium, an inert, harmless gas. Its main drawback is that reactor walls become irradiated by high-energy neutrons and will eventually need replacement. But compared to fission's long-lived waste, fusion's footprint is far lighter. In terms of raw energy, both are staggering. A kilogram of uranium undergoing fission can release as much energy as burning thousands of tons of coal. But a kilogram of hydrogen isotopes undergoing fusion dwarfs even that, offering nearly 4 times more energy per unit mass. Fusion is the deeper tap into the nuclear wellspring, the very process that powers stars for billions of years. Safety is also a dividing line. Fission chain reactions can spiral out of control if cooling systems fail. As history has shown at Chernobyl and Fukushima, fusion is intrinsically different. If conditions slip, the plasma simply fizzles out. There is no risk of a runaway chain reaction. The danger lies not in catastrophic meltdown, but in the technical difficulty of sustaining the reaction at all. Technology status is perhaps the starkest contrast. Fission is mature. Today, about 10% of the world's electricity comes from nuclear power plants. Fusion, by comparison, remains experimental. Decades of research have produced remarkable progress, but no commercial fusion plant yet exists. Humanity is caught between the fire we already command and the fire we are still chasing. This showdown is not just scientific, it is symbolic. Fission represents the nuclear age we know: powerful, feared, and flawed. Fusion embodies the future: clean, limitless, and just out of reach. One split the atom, the other could let us harness the stars. The contest between fission and fusion is not just about the present. It's about where humanity goes next. Both technologies continue to evolve, but along very different paths. Fission, though older, is far from obsolete. Engineers are developing small modular reactors, compact units designed to be safer, cheaper, and easier to deploy. Unlike sprawling nuclear plants of the mid-20th century, these reactors could power remote communities. supply industries, or even support lunar and Martian bases. New designs like molten salt reactors or fast breeders aim to consume more of their own fuel, reduce waste, and lower the risk of accidents. Fission's reputation may be scarred, but its potential is still formidable. Fusion, meanwhile, stands as the great scientific promise. The multinational ITER project in France is assembling the world's largest tokamak, designed to demonstrate that sustained, net-positive fusion is possible. In the United States, the National Ignition Facility reached a symbolic breakthrough in 2022, achieving ignition with powerful lasers. A glimpse of what might one day power grids. Beyond these giants, private companies are racing with bold alternatives: compact reactors using high-temperature superconductors, pulsed systems relying on magnetized targets, or even approaches inspired by astrophysics. Billions of dollars are flowing into ventures once dismissed as impossible. The implications reach far beyond Earth. Fission reactors could provide steady power for space colonies or drive nuclear thermal rockets, cutting travel time to Mars by half. But fusion holds the keys to something grander: deep space propulsion. A working fusion drive could shorten interplanetary journeys to weeks and make interstellar probes feasible within a human lifetime. The same fire that lights the stars could, one day, carry humanity to them. Still, obstacles remain. Fission must confront political resistance, safety concerns, and the unsolved problem of waste storage. Fusion must cross the immense engineering gap between experimental success and reliable power plants that run for years, not seconds. Both paths are fraught with challenge, but both could redefine how civilizations live and expand. The future of power is not only a technical question, it is a question of will. Which fire will humanity choose to carry into the centuries ahead? The controlled splitting of the atom, or the bottled light of the stars? Fission and fusion are more than scientific processes. They are symbols of where humanity stands in its relationship with power. Fission gave us the nuclear age, reactors that light our cities, but also weapons that could erase them. It is a fire we hold uneasily, knowing its dangers as well as its benefits. Fusion remains the fire of the stars. We have glimpsed its destructive potential in hydrogen bombs, but its peaceful promise, clean, abundant energy without the shadow of waste, has not yet been realized. For decades, it has hovered just beyond our grasp, demanding new science, new engineering, and perhaps a new level of human cooperation. Together, they form a paradox. One is real but feared. The other is ideal but elusive. One split the atom, the other could let us harness the stars. Both remind us of the double edge of discovery: the power to save and the power to destroy. We stand between these two fires, shaping our future by the choices we make today. Will humanity continue to live with fission, refining it into something safer? Or will we rise to the challenge of fusion, learning to bottle the energy of the cosmos itself? So, which path should humanity prioritize? The proven power of next-generation fission, or the stellar dream of fusion? Let us know what you think in the comments below. And for more explorations into the science that will shape our future, make sure to subscribe to Scientific Facts.